So Ian is in the gravity group in the Southampton maths department, and he is very gladly decided to come and talk to you guys tonight instead of staying in and having a nice evening in. So everybody thank Ian, and I shall pass you straight over.
Thank you very much, and thank you all for coming along. So, a slightly cryptic title to my talk, Einstein's Secret Universe, so secret that it's difficult to figure out what it's about from that. Let me take you back, not all that long ago, to February the 11th, 2016, and on that day, another big scientific result was announced. It was the detection of gravitational waves, and you can see, I hope you can see, two scruffy little lines on that plot there. So those lines represent the stretching and squeezing of space caused by two black holes colliding and coalescing to form one black hole 1.3 billion years ago. So this is a story about a different sort of wave from the last talk about gravitational waves. And what I first want to do is say a little bit about why this was big news. I don't know how many of you can remember that day. I can for obvious reasons, but this story led on the 6 o'clock, the 10 o'clock BBC News programmes. The newspapers went with it. The Independent devoted almost the entirety of its front page to this story. So this is an image of two black holes with a starry background. There's a bit of science in that image. The starry background behind is being lensed and distorted by the powerful gravity. It's done on a computer, obviously, that image, but it's illustrating a point. The headline was, "The theory of relativity proved." Well, that's a bit strong. I mean, we don't prove stuff, right? Sometimes, if we're lucky, we disprove things, but it was nevertheless a big deal. This was the front page of the Daily Telegraph. This is a slightly less scientific picture. It's a glossy picture of a black hole spewing out a jet. To give you an indication of how seriously the Telegraph were taking it, only about 20% of the front page was devoted to an anti-EU story. And you can't possibly see this, but there's just a tiny little thing there about Downton Abbey, which was their big obsession at the time. So that was, they clearly thought this was an important story. So I didn't see this, but apparently the big issue had something about this on the cover as well. The space doll making gravitational waves. Apparently the actual item itself didn't really have much to do with gravitational waves, but they made use of it. And you can just see Einstein at the top sticking his tongue out at us saying, "I told you so." And then, this is a video. So before you play it, I should explain one thing. So this wave signal here, it's not a sound wave, it's a gravitational wave, but it so happens the frequency of that wave isn't so different from the frequency that we're sensitive to with the human ear. And what people have played around with is taking that gravitational wave and converting it into a sound wave. So if I go forward, can we then see if we can play the video? So this is a rap song in which that actual wave, the real wave, is sampled into it. It's a little chirp sound.
Just black hole. Hear you all. Just black hole. I want to hear you all.
So there won't be any more of that. Could you hear that little? And by the way, if the sound hadn't worked, I wasn't going to sing it for you. Did you hear that little chirping sound? Something that starts off at low frequency and increases in frequency. That's the actual audio equivalent of that gravitational wave signal. So what I want to do in this talk is to say, what are gravitational waves? And why was this detection by the so-called LIGO detectors, that's the name of the detectors that found these things, why was it such a big deal? And this story actually goes back a very long way indeed. It goes back, in fact, 101 years to 1915, when Einstein published his theory of general relativity. So this is basically a theory of gravity, about how things move and how gravitational fields distort space and time. And there are all sorts of interesting things about general relativity, but one of the important things, and the thing that's important for the story I want to tell you today, is that just like special relativity that came 10 years before it, there's an absolute speed limit in general relativity, which is the speed of light. Nothing can go faster than the speed of light. And that's important for two reasons. So, first of all, the fact that things can't go faster than light means that you could imagine that if you pile enough mass together in a small enough space, then something that travels even as fast as light wouldn't be able to escape. That's a hand-waving sort of justification or plausibility argument for the existence of black holes. Now, it was in 1916, just 1 year after Einstein published his theory, that people came up with the mathematical solution that corresponded to this. For many years, people didn't take it seriously, but then in the 60s and 70s, astronomers began to see things that they thought were black holes, and now we see all sorts of black holes, and we don't see them directly because they're black holes, but we see their effects on things around them. So maybe if we could now play, so this is a video as well, if we could play this. This is the location of what's believed to be a supermassive black hole at the center of our galaxy, and these little dots are stars that are moving around. So if we just trace that star there, it gets close to at the center of the galaxy, and then it shoots around. If you look at this purple one, it will do a similar thing. So these are stars that seem to be orbiting around some unseen mass at the center of our galaxy. And if you try and figure out what that mass is, because you can do that by looking at how those stars are moving, you come up with a mass of something like 4 million times the mass of our sun. So there's some very dense object there, and we think it must be a black hole, because if it's not a black hole, we can't think of anything else that it possibly could be. So it's not really a proof that black holes exist, but it's a plausibility argument. So that's the first thing. The second consequence of nothing being able to go faster than the speed of light are the gravitational waves themselves. So everything produces gravity. Me standing here now produces a gravitational field. If I move my arms around, I'll just move my right arm around, if I move my arm around, I'll produce some gravitational waves. Why? Because if nothing can go faster than the speed of light, well, that speed limit even applies to gravity itself. And 100 years ago, 1916, Einstein looked at the mathematics of his theory, and he saw exactly that. The little ripples in the gravitational field will indeed propagate as gravitational waves. They go at the speed of light, and they've got all the sorts of properties of waves that we were, in fact, just hearing about from Hendrik. So that's the second thing that's important. So we have some idea that black holes exist and gravitational waves. And in fact, with the gravitational waves, we since the 80s and 90s have had some, again, indirect evidence that Einstein was right. Why? Because we've seen two stars in our galaxy in a binary system, so one star orbiting the other, that are very, very gradually spiraling in toward one another. And that's happening because those stars are themselves emitting gravitational waves. They're carrying away energy, and that's causing the orbit to shrink, and it's shrinking at just the right rate, as predicted by Einstein's theory of relativity. And that's something that's being shown by this data plot here. Basically, it's showing that the orbit is shrinking in just the way that Einstein's theory would have predicted. In fact, the talk after mine by my colleague Emma, she'll talk a bit more about how things actually produce gravitational waves, but the point is, all systems work at some level. So that's where we were. As of a few years ago, we had some indirect evidence that black holes were real, and we had some indirect evidence that gravitational waves were real, but of course you want to do better than that. We'd actually like to detect those gravitational waves, and maybe even detect gravitational waves from black holes. So the question is, how can you detect a gravitational wave? Well, the gravitational waves passing through us all the time. They're so weak you can't feel them, but they're passing through us. And if you look, and Einstein soon realized this, if you look at the equations of his theory, what gravitational waves do and make things oscillate ever so slightly. So these gravitational waves that are passing through us are exerting tiny little forces on us that are tending to make us shake ever so slightly. So that's the game. If you can build a detector that you can isolate from all the sources of seismic noise, all the sources of vibration here on Earth, so it's really, really still, really stable, and then if it suddenly starts shaking, you can say, the gravitational wave has passed through my detector. And people took that idea seriously, and this is a picture of Joseph Weber, who started building gravitational wave detectors in the 1960s. And what he did was basically build big bars of metal, and try and hang them, isolate them from noise, and he claimed to detect gravitational waves. And this is a real controversy. Other groups immediately tried to follow his example, and no one could produce his gravitational waves and his detections. And it soon became clear he was just seeing noise, he was just seeing junk. But to the day he died, he was sure that he detected gravitational waves. Now, we're now confident he couldn't possibly have detected them. And in part, it's because his bar was so small. If he could have built a bar that was twice as long, the shaking effect he was looking for would have been twice as big. If he could have built one that was 10 times as long, it would have been 10 times as big. But, of course, there's a practical limitation in how large a bar you can build. And so what people realized was that there's a better way, a completely different way of trying to detect gravitational waves. And this, in fact, exploits light waves, and it exploits many of the ideas that Hendrik talked about in his last talk. So the idea is this. We're going to look at what's called an interferometer. So the idea is we're going to have a powerful laser at one point in our apparatus and a mirror, and the laser is going to fire light at that mirror. Half of the light is going to go down one half of an L shape. The other half of the light is going to go down the other half of the L shape. At the ends of this L shape, there are mirrors which are just suspended. So these are playing the roles of little particles. And the idea is that as we shine the light back and forth, it bounces back, and then we recombine the light here. And when it recombines there, we'll get an interference pattern. In fact, so this is a video. Maybe we can start playing it now, because I've had a head start on it. And so the laser is shining the light up and down the two halves of the L, but the crucial thing is this: if a gravitational wave comes along, it makes the whole thing shake, and that's going to change the distances that the light has to travel up and down the two arms. So here you can see the light going down one of the arms, it's bouncing off the mirror, it's travelling back, exactly the same thing's going on in the other half of the L shape, then we're recombining our beams, and then precisely the thing that Hendrik spoke about of getting either constructive or destructive interference. Well, we're getting that sort of interference here. This is where we read out the result of our experiment. And if we zoom in just a moment, the point is this: whether or not we get constructive or destructive interference depends on the exact distance that the lights have to travel up and down these arms. So if there's a gravitational wave coming through, it's going to be moving these two arms differently, and it's going to produce a time-varying interference pattern there. And the point is, because these are lasers firing down tubes, you can make this really big. So how big? Well, let me get back to the experiment that made this detection. It's the so-called LIGO experiment. So LIGO is an acronym. It stands for Laser Interferometer Gravitational Wave Observatory, because it's using a laser. The device I just described is a laser interferometer. It's designed to detect gravitational waves. And get this, so the laser is in this so-called corner station here. This is a detector that's in Hanford in the United States. This is one of the arms of the detector. It's 4 kilometers long. And there's another arm going off on the other side here. You can only see a little bit of it. That's also 4 kilometers long. So Joseph Weber had 1 meter to play with. Here there's 4 kilometers. So the effect of a gravitational wave on this will be much bigger. You've got a better chance of detecting the gravitational waves. There are in fact 2 LIGO detectors in America. One in Hanford, which is the top northwestern corner, and there's another one in Livingston in Louisiana at the bottom southwest. Southeast. And having 2 makes it easier to detect gravitational waves, because you can look for coincidences between those 2 detectors. So what actually happened? So what happened was, so these LIGO detectors first started taking data around about the year 2002. They took data to about 2010, and sadly, we saw nothing. We just produced loads of upper limits. We didn't detect anything. They were then shut down. 5 minutes? They were then shut down and upgraded to the so-called advanced detectors. And then in 2015, within 2 days, just 2 days of the advanced detectors coming online, something extraordinary happened. This is a signal in the gravitational wave readout that arrived at the Hanford detector. It's a little wave that starts off small at low frequency, and gets louder, and its frequency increases as time goes by. There was a similar signal observed at the Livingston detector, but 7 milliseconds earlier. That's the light crossing time, or the gravitational wave crossing time between those two sites. And if you time shift them, they actually match up very well. And they don't just match up with one another, they match up with the exact mathematical predictions of Einstein's theory of general relativity, if you believe that this was a signal produced by two black holes coming together in spiraling and forming a single black hole. So that happened in September 2015. The announcement, I said, was in February, so that was about 6 months later. Of course, there was a lot of careful checking that had to be done, and one of the things that was done was to learn as much about this binary as possible. So, well, let me get to that in a moment. So this is the something that's dear to my heart. This is the actual detection paper, Observation of Gravitational Waves from a Binary Black Hole Merger. If you Google it, you'll find it. It's actually really well written. You can, by all means, have a look. Here's the author list. B.P. Abbott et al. So the first author's surname is Abbott. You can't see from there. The second author's surname is Abbott. The third author's surname is Abbott. This is a really large, they're not relatives, as far as I know. This is a really big collaboration. And in fact, not long before that, the leading author, it was alphabetical, was Abadi, A-B-A. And before that, the leading author was Arsi, A-A-S-I. So there were 1,004 of us on this detection paper, which is one of the reasons why it took 6 months, but it's not the main reason. So what was actually detected? Well, it was two black holes coming together. One had a mass, and you can read it off from the abstract, of 36 times the mass of the Sun. The other had a mass of 29 times the mass of the Sun. The final black hole that was produced, because they came together to form one spinning black hole, had a mass of 62 solar masses. If you do some arithmetic, the numbers don't add up. Well, that's not an error. The equivalent of 3 times the mass of the Sun was radiated in gravitational waves. This is the most luminous event we've ever observed. Okay, this was extraordinary. It was still very weak when it reached us, but it was an incredibly powerful event with lots of energy produced. So why was this a big deal? Well, it's a big deal for 2 reasons. First of all, this really is vindicating Einstein's theory of relativity. It was arguably the outstanding prediction that hadn't been directly verified from his theory, the existence of gravitational waves. It also verified that black holes exist and have the properties that he predicted. But then this was also a big deal for astrophysics, and Emma's going to say more about this in her talk, but basically we've got a new way now of looking at the universe. It's not light, it's gravitational waves, all right? So what have we got coming up in the near future? Well, I've talked about the 2 American detectors, the LIGO detectors. This is a map of the world. There's going to be an Italian-German detector coming online later this year, and the Japanese have got one in the pipeline as well. Further down the line, there'll be another one in India. There'll be more detectors, and there'll be better detectors. We'll be able to detect weaker signals and therefore detect things more often. And hopefully, we'll see some new things. This is a picture of the star exploding. Who knows, we might see that sort of thing in gravitational waves. But whenever we've looked at the universe in a completely new way before, we've also had some surprises, and I hope there will be this time as well. Thank you.
Thanks, Ian, that was great. Any questions for Ian? Okay, no, question over here,
Is the wavelength of light affected by gravity waves? I assume not.
So,
What was the question?
yeah, I'll repeat the question. So, is the wavelength of light affected by gravitational waves?
Good question.
So, yeah, I think that the simple answer is yes. So what gravitational waves, I didn't put it in my talk, but what gravitational waves do is tend to change the separation between freely floating particles. And we normally talk about it in terms of massive particles, so nothing to do with light, just like, you know, little particles. But gravitational waves will have an effect on light as well. And so the stretching of space-time, because of something called the equivalence principle, has to affect light as well as affecting matter. Does that answer your question?
So it doesn't mean it negates...
Okay, so this is the most difficult question that anyone could possibly ask me after this. And great minds have spent a long time trying to give really neat, simple answers, and so let me repeat the question in my own way. So what I've said was we're detecting gravitational waves by bouncing laser beams, so bouncing light in an L shape and recombining them. And the worry is, of course, that if the light is getting stretched in proportion to everything else, then there'll be a cancellation of the effect. So that doesn't happen. It's difficult to give a very simple explanation why, except that the effect is not. It's not identical, the effect of the gravitational wave on the whole sort of distributed laser beam as it is on just that single particle. So there isn't a cancellation. I don't have a very simple explanation though as to make it any simpler than that, but that's the famous question about gravitational wave detectors.
Very good. Well done. And in fact, that was going to be my question to Ian if none of you came up with anything, so you're going to get a t-shirt for stealing my question. But are there any others from the room? Yeah, go on. Was it John?
John, yeah.
Excellent, yeah.
So, tying up the first talk, what would the quanta of these gravitational waves be, and what would it take to discover them?
Okay, so what are the quanta? Of course, so we heard about photons and particles in the first talk. So people talk of the graviton as this hypothetical particle that would correspond to a gravitational wave. So they've got a name, that's something. It goes without saying, no one's ever detected them. So how could you detect them? So I don't think there's anything on the near horizon for detecting them directly. So the issue with gravity is it's incredibly weak, and all the experiments we do are very well described. It's just classical wave-like picture. I'm not aware of any real experiments to probe the graviton nature of the gravitational field. So it's got a name, but not an awful lot more, I fear.
Thank you. So I know we've got a few more questions. So we've got a question here, we've got a question over here, so we'll go to him first.
So I was just trying to understand the timescale for the frequency chart that you've showed us. So these two stars, they've been orbiting around each other for a little while, and then we're just seeing the very last fractions of a second as they finally come together as a black hole.
Yeah, yeah.
And it's a one-off event, and that's it. If you didn't see it, you missed it.
Yeah, so let me repeat the essence of the question. So what are the timescales here? So this pair of black holes will have existed for many, many millions of years prior to us detecting them. The actual signal that we saw lasted about 0.3 seconds. In other words, we could only see the last 0.3 seconds of the life of this binary. The actual gravitational wave detectors themselves have got a certain... they're sensitive to gravitational wave frequencies between a few tens of hertz and about a kilohertz. And so what I just said is equivalent to saying that when this system first entered the low frequency end of our sensitivity band, and the time to it merging within our sensitivity band, that was about 0.3 seconds, and when it merged it had a gravitational wave frequency of about 170 hertz, I think it was something like that. It's a one-off thing, because once those two black holes have come together, you've then just got one spinning black hole, but it's just spinning really steadily. It's I don't want to say it's boring, because I shouldn't say black holes are boring, but it's not, it settles down and doesn't emit gravitational waves anymore. So the trick with these events is to catch them when they happen, and they're weak, they're difficult to see in the data, and you've got to be looking out for as much time as you can to see them.
And presumably you've got no idea where in space this signal has come from. You just know somewhere out there it is happening.
That's right, we've no idea which particular direction to look in, because these things are coming not from our own galaxy, but from very far away. So this was from 1.3 billion light years away. And so because we're looking on large scales, and because the universe is roughly the same on those large scales in all the different directions, you've got to be prepared for the signal coming from any direction in the sky and at any time.
Fantastic. So I did see a question down here. Yeah, if you want to go, that's great.
I was wondering, since it's theorised that black holes form by absorbing other black holes, will we ever be able to detect gravitational waves from our own galaxy? Like the black hole? Yeah.
Right. Yeah, so will we be able to detect gravitational waves from our own galaxy? Well, there are plenty of binary star systems in our galaxy, and there may well be binary black hole systems, although we don't know of any. The trouble is that these events, if you just look at one galaxy, don't happen very often. We think they happen like once every 100,000 years, something like that. In fact, we're going to get a much better idea once we've collected more data how often they happen. But the fact is, from any one galaxy, so from our galaxy, these events, these binary inspirals would happen so rarely that there's no realistic chance of seeing them. We've got to look to large volumes of space containing many galaxies to have what we call a good event rate, so we know a reasonable probability of seeing these events while our detector's in operation. Yeah, so my answer was more about the small black holes and inspiring. So yes, I even showed you a video. There's a supermassive black hole at the centre of our galaxy, and other stars will fall into it. Again, it's quite rare that they would produce strong gravitational waves, but even if they did, the frequency that you get out from something falling into a black hole is basically determined by the mass of that black hole. And for a very big, very massive black hole, it turns out that that frequency is very low, and it's much less than the 20 or so hertz below which our detectors are completely swamped by seismic noise. And so you need to look to putting a detector up in space, and there are hopes to do that, the so-called LISA project, to see black holes, to see little black holes, say, falling into big black holes.
Fantastic. So question back here and question over here, so we'll go with you first.
Just intrigued about the time scale. You said that after 2 days of turning it on, do you see the black holes they're coming together and then turn it on in time for that, or do you see the gravitational wave and then look for what would cause it?
So, if I've understood you correctly, you're asking about, so we turned our detectors on and we were just lucky that it happened 2 days later. It was just coincidence, okay?
And you weren't looking for what could cause the gravitational wave?
So not really, because the only reason we were able to detect them in the first place is that we were looking for them. So these signals are quite weak, and the way you can pull out very weak signals from noisy data is to have a model of what the signal looks like in the first place, and then you keep comparing the output of your detector with that model, and there's a way of mathematically sort of combining the model with the data so that you can do it in an automated way. So it's only because we were looking for these signals with the precise form predicted by Einstein, and we weren't just looking, of course, for black holes with mass 29 and 36 solar masses. There was a huge array of templates, vast number of templates, i.e. different waveforms for different mass black holes, and they were all being searched all the time over the data. And it's because we had a good match in our template bank to the actual signal that we're able to make the detection.
And I guess, do gravitational waves travel at the speed of light?
They do. They've got lots of properties, well, they've got several properties in common with light waves. They travel at the speed of light, and they also have an analogue of polarizations, which is something to do with the geometry of how they affect the things that they move through.
So there's no way we could see something first and then think, oh, we'll turn LIGO on to detect the wave, because, yeah, it would arrive at the same time. Fantastic. Yeah, question over here.
How do you know that from 1.3 billion light years?
Yeah, so how do we know that from 1.3 billion light years away? So it actually relates very closely to what I said about templates. So you use Einstein's theory to predict what the signal would look like, and so by seeing what the frequency is and how it evolves in time, you can see which of your templates corresponds to that. And so we knew it was a 29 and 36 solar mass black hole, but we also knew how strong the signal was. And the point is that the signal, if you move the black holes further away, the signal gets weaker and weaker. If you move those two black holes twice as far away, the signal's only half as strong. So because we knew the absolute size of this wave in our detector, that also gave us this distance information.
Fantastic. So Ian's been very popular. I think no more questions, which is just as well. So we've just about out of time for a 5-minute break for Ian. Emma, rather. So thank you very much, Ian.